Hello, everybody. Thanks, Philip. So my name is Gwendolin Wilke, and I want to shift the focus back for you to electricity, to have a bit of bias in this session. I want to talk to you about load forecasting, power load forecasting solution that we developed as part of an AeroNet project during my time at Lucerne University of Applied Sciences. I just switched universities. I want to give you a very brief overview over the project context itself and then about the load forecasting solution that we developed. If we project 20 to 30 years in the future, what we can foresee is that the power grid, as we have already heard, will have massive capacity problems, or we can envisage that it will happen if we do not expand the power grid in a very large scale. So one of the main reasons that this is envisaged to happen is that we will have a high or very strong increase in simultaneity in production, which is due to the proliferation of new renewable energy sources in the grid. And we will also have an increase in simultaneity in the consumption. Oh, wrong. In the consumption, which is due or which can be attributed to the fact that we will have an electrification of the power grid or of the grid itself, energy grid itself. Basically also due to sector coupling techniques and an increase in that. So since we know that grid expansion is very expensive, it is very important that we try to find intelligent solutions to use the existing grid capacity better. And these solutions should use market-based principles, which basically means we want to have market-based or financial incentives for customers, but also for other stakeholders that allow them to do it on their own terms and for their own good, and not have regular decisions enforced from top down. In order to achieve this, the project developed a business model as well as a technical solution to use part of the grid capacity that is currently unused and reserved for contingencies, which is usually termed N-1 security of supply. And the idea is to use it for a very special type of, or to define, what we did is define a special type of flexible loads that are also envisaged in the future to not be critically dependent on N-1 security of supply, and on the other hand are main drivers for causing capacity problems in the grid in the future. So the market-based solution that should be provided here is the basic principle behind is that we do not only want to optimize the grid, but at the same time want to optimize spot prices for industrial customers. The project was focused on mid-voltage grid, so our main audience in terms of customers were industry customers. One of the work packages of this project is the day-ahead load prediction of regular loads, not of the flexible loads that should be optimized here, but of the regular customer loads that are subject to N-1 security of supply. And the goal of this was to not only use be able to not only use the fixed capacity band that is unused currently, but also to be able to even more utilize the unused grid capacity by providing a dynamic capacity band for use of the new loads. So what were the preconditions for this? As I said, we were in the medium voltage grid, and we're dealing mostly with industry customers. Industry customers usually have a very different characteristic of load profiles, and they are very often highly volatile, which is due to the fact that the context data that is needed, that provides information about processes, production processes that drive decisions to change schedules, are not provided by the utilities and by the industry customers, because it's just simply too difficult or too much effort to collect and to monitor. The requirements for the prediction model were to deploy the solution locally at the premise on site at the customer's site. So do a local prediction and not an aggregated prediction. We also wanted to have an out-of-the-box solution so that we do not have to customize the model that we develop for the customer themselves, or have manual parameterizations or customizations to be done. And the third requirement, or R2, second requirement actually, is to have virtually full coverage. So the major part of all the customers should get a prediction that is reliable enough and accurate enough for them to be useful, or for us to be useful in the project. So we want to cover most of our customers and not have a lot of them being forced to enter the stuff manually or exclude them from the project. The data set that we were provided was historical time series data for 35 end nodes over 1 year, and with at least 200 kilowatt of power demand. And the sampling intervals were 15 minutes. So in order to allow for requirement 1 to work, we chose to use just a brute force approach, like a model selection approach, where we applied 18 different models with, again, different parameterizations to each of the customers, selected the best ones for them, and hoped that that would do the job, which actually did, more or less. What happened, probably before I tell you this, what models did we include in this model selection approach? It consisted of a lot of very simple models that are usually mostly used for this. If we only have time series data and no context data, this is what the experience tells us that works best for most of the customers. So we had a benchmark model which just used the same time series from yesterday or the day before. Some similar days used in some way. Then the usual time series prediction models like Hold Winters and Random Walk with Drift and ARIMA and GARCH. And then we had several machine learning models, basically SVR, support vector machines, and different neural network models. And here on the right-hand side, you see the model selection, which means the different bars here that you can see are the different sliding window lengths used for training data, and which is very awkward when we didn't figure out why. There is not much of a difference how long we train the model. This is one of the further work to do. What was not very surprising is that adding, what you see here is adding models of increasing complexity to the model selection approach, and the resulting MAPE, or mean average percentage error. And what's not very surprising is that adding more complex models doesn't help very much in terms of MAPE. But it helps a lot, and that you can see here. It helps in decreasing the spread of the data, of the MAPE, of the accuracy over the customers. So this is actually why we chose it, because it facilitates the second requirement to have a virtually full coverage of our customer base. If you look at this picture, what you see is what models have been selected. And here you can see that indeed the very, very simple models, simplistic models, have been chosen most of the time. But sometimes other models have been chosen. And in this case, the accuracy increase, so this is the comparison with one of the similar days models, one of the very simple ones. Some customers have, if another model is chosen, the MAPE can increase or decrease actually very, very strongly. Accuracy can increase very strongly. So what this brute force approach basically does is trade the ubiquitousness of the model or the universality of the model against computing effort. And I just want to mention very quickly reliability. So the reliability of the model is pivotal for our customers, of course. We don't want to have very big errors in that or a lot of errors. Since we don't have, in our errors are not normally distributed, we did a reliability check manually, not manually, but which turned out to be fine. And also we did some simulations to find out if actually the prediction really helps or how much it would help in order to have, to utilize more of the capacity band than the fixed bandwidth approach here. And we found in the simulation it was an increase of 16% compared to this approach. So it actually does help and is useful to apply. Yeah, so basically this brute force approach does comply with the requirements of the project. With the implementation, we could mitigate a bit the problems that we have with computing efficiency by throwing out some of the models that are never used or only trying them once in a while to check. And further work includes, as I said, finding out why some of the parameters doesn't impact the model, including more context data and playing around with that if we should get them. And finding out, one of the issues is also that the stability of the model in terms of which model is selected for a certain customer is not very strong, and we would like to do more tests on that. Yeah, so I would like to thank you very much. If you have any questions, please come to me later in the coffee break or in the session afterwards. Many thanks.